All right, AP, welcome back. Let's practice some more entropy calculations. Now, how do we calculate entropy in a chemical reaction? So absolute entropy or entropy change. Recall that delta F or delta H, little f, remember that F means formation. So formation, when we would take an element and make 1 mole of the compound, when we looked at the delta H values on our appendix, we didn't have to look them up for pure elements because pure elements were all zero. So like carbon, N2O2, we didn't have to look them up. They were all zeros. It's not the same for entropy. And the reason why is because all states of matter have movement. The question is how much movement do they have? So unfortunately, when it comes to our appendix values, we need to look up every chemical's entropy. You know AP will not give you a 3-page document of entropy values. They'll give you a small data table, and I'll show you right below so you get a little sneak peek. Something like this, very small. You'll just have to look up whatever values you need. Okay? So let's get back to it. So why? Because every chemical compound, every molecule, they all have movement. Some have more than others, but they all have movement. So all of these delta S values, they should all be positive, okay? Because everybody has movements. Every state of matter, doesn't matter the compound, it all has movement. Just some are higher than others. So when you see low delta S values, they have low movement. So probably like solids. When you see very high delta S values, okay, that means they have a lot of movement. So like gases, okay. So the only substance that has an entropy value of 0 would be if it actually is, remember, third law, thermodynamics, a perfect pure crystal at 0 Kelvin would have a value of 0. You're not going to find one on the appendix because we're not talking about perfect pure crystals at 0 Kelvin. So to calculate your delta S probably looks very familiar to you when you did delta H. We're going to do the products or the reactants. Make sure, beware of coefficients. Okay? You got to take the value and multiply the coefficients out. So standard we know is 25 degrees Celsius, 1 atm. Molar, because we're going to have units of moles, and then entropy, delta S. Whether you write the word reaction or not, that's your choice. Sometimes you may see it without. It has the units of joules, moles, times Kelvin. Notice the difference between delta S or delta H, joules versus kilojoules. That's it. And also with delta H, you have no Kelvin when it comes to delta H because we're not putting temperature into the calculation. Some observations that you already know. Entropies for gases are the greatest compared to liquids and solids. Gases are more spread out. They have more space to move. So see the table below for water. We'll scroll down in just a second. Delta S values tend to increase with molar mass. And the reason why is because they have maybe more bonds, more electrons. Remember, electrons have mass, very little, but they do have mass. And they have more degrees of freedom. So like H2 versus N2 gas, okay? You have something that has a molar mass of 2 versus 28, okay? Definitely entropy is greater for that N2. Entropy tends to increase with more atoms in the formula. So like if you had O2 versus something called ozone, which is O3, kind of correlates to molar mass 2, also correlates to bonds, okay? So you will have more entropy pretty much the bigger it is, okay? First AP, I have 2 examples for you. One, can you predict entropy just by looking at the balance equation? Will it be positive or negative? And then explain, but using entropy with movement, okay? So I gave you the very first one. N2H2 gives you ammonia, okay? Remember there was something about entropy about the more gaseous moles that you produce create movement. Okay? I have 1 mole of gas versus 3. So right here, I have 4 moles of gas versus 2. Okay? I have restricted movement because I went from a lot of movement, particle movement, 4 moles of gas to 2. I have constricted it. So I'm predicting when I do my delta S reaction, delta S, I put my little degree sign too, products minus reactants, okay? My products, I have 2 moles versus 4. I'm going to be assuming it's going to be negative. And the reason why is because I have less moles of gas that have formed, and now I have less freeing particles that can move about in that space, okay? If they're still gases, I have 2 ozone, remember that's ozone, versus oxygen gas. But I have 2 moles versus 3. I'm definitely going to increase. I'm going to type it instead. So increase, and I'm predicting the sign will be positive, okay, because I have created more gases to move freely throughout the container or whatever it is that it's in. Okay. Remember, you could talk about they're more dispersed. You can talk about more particle movement. Okay. So when in doubt, refer to the beginning of this chapter, 19.1 to 19.2. Okay. How to explain. Okay. Remember AP's tip on how to explain. Okay. If I have liquid water versus gas water, well, I already know states of matter. I know this gas is going to create more movement than that liquid. Okay. So same thing. I'm going to increase. I created more gas. So actually, we're going to go. Let's go back up to the AP tip. Remember, is the one about taking the solid. Okay. Particles are more free to move about as opposed to the solid form. I like that. Let's use that one. So let's go back. Okay, so it's definitely going to increase. Okay, particles are more free to move around in a gas phase opposed to a liquid phase. Okay, pretty simple enough. I have 2 solids versus a gas, and I produce 2 solids. Okay, well, even though I have 3 moles of particles here, I have a gas. And now I went to a solid. I've restricted movement. I'm definitely going to be decreasing. So you can even mention what was mentioned here, negative. Oops, let me get rid of that circle. Because I have less freely moving particles in the solid phase. There you go. Okay. So less moles of gas are formed and less freely moving particles in the solid phases. Okay. Pay attention to gases first. So the things you want to focus on are states of matters. Okay. Gases give you the most movements versus liquids and solid. Then what if there's a tiebreaker? If there's a tiebreaker, look at moles. Look at weight, molar mass. Actually, I like to put molar mass, not weight. Okay, same thing that we just mentioned up here. Notice the formula. Do you have more atoms in the formula? More molar mass in the formula? What do you have more of? Okay, So let's actually practice if our predictions are correct. So this very first one, we said our answer is going to be negative for the production of ammonia. Let's actually calculate it. So I included the delta S values above. Okay, so we're going to take our delta S reaction, and we're going to take the delta S, the sum of all the products, and the delta S, sum of all the reactants. Well, I already wrote my equation right here. I don't have to keep writing it over and over. Show your work, show your unit, show your sig figs. So I have N2, because remember, we have to look up every value. Okay, there is no zero for elemental form when it comes to delta S. We got to look them all up. So I have N2, I know it's going to be 191.5. I have H2 right here, and then I have ammonia, and it's all in gases. So I'm going to say my delta S reaction, okay? My one product that I have right here, my 2 times this. So I'm going to put my work right here, 2 times 192.5. And remember, this is joules, moles, K. All right. So I'm going to put my answer down there. And notice all of these values, they're all positive values. And why? Because all states of matters have motion, have movement. Okay. So my N2, I only have 1 mole of that. So I'm going to say 191.5 joules, moles, K. And then my hydrogen, I got to multiply by 3. 130.6 joules mole K. All right, so let's multiply this out. So the only product that I have is that 2 times 192.5. So my product I have is 385 joules mole dot K. And I'm going to subtract that with, and I got to multiply the hydrogen out first. So 3 times 130.6. So this right here down below, I get 391.8. Well, I'm going to add these two values up, 191.5, and then that's what I'm going to subtract because that's my reactants. So 583.3 joules moles dot K. So I'm going to take that 385, and actually I need to fix my sig figs. You're probably yelling at Rodriguez on the other side of this camera. Right there, that sig fig counts. So I do need to put 0.0 right there. So 380.0 minus 583.3. I'm going to keep my 1 after the decimal. Negative 198.3 J mole dot K. Make sure you box that. And remember our prediction. We said it would be negative because I formed less gases compared to the reactant side. And look what happened. We were negative, and double checking our negative over here. Good job, good job. So I would like you to do the next 3. Use the blue to check your answers. And then after that, I'll see you on the next one.